As physicists, we've enthusiastically guessed this second for more than a century. Beginning around 1916, this occasion denotes a momentous accomplishment, offering a brief look into one of the universe's most charming and confounding peculiarities: dark openings. These enormous Goliaths, known for their tremendous influence, remain staggeringly tricky. While they are huge in terms of their gravitational impact, they are almost imperceptible to us, making them considerably more mysterious. One such dark opening, possibly gauging between 2 to 4 million times the mass of our Sun, may be the subject of this disclosure. Throughout recent decades, the examination devoted to dark openings has changed our comprehension, taking us from a place of outright obliviousness to one where we are beginning to get a private gander at them. And presently, things have taken a much more exciting turn, as physicist Michio Kaku has uncovered that we have at last figured out how to look inside a dark opening. This discovery makes way for an abundance of new data that could enlighten parts of science we may have previously disregarded. Let us take a deep dive into the domain of dark openings and uncover what exists within them. While space is unfathomable and tremendous, the idea of dark openings brings up endless issues. Before we plunge into the specifics of Kaku's exceptional findings, it's essential to comprehend the fundamental concept of dark openings. Many people have a basic understanding of what dark openings are, but significant gaps in our knowledge still remain. The theory of dark openings traces all the way back to 1916 when Albert Einstein published his general theory of relativity. This theory predicted the presence of dark openings. However, at the time, the idea was purely theoretical. It was only about 50 years later, during the 1960s, that substantial evidence for their existence began to surface. Researchers studying the constellation known as Cygnus observed an unusually bright blue star emitting X-rays. They discovered that this star was not stationary but was instead orbiting a massive dark object. Upon further investigation, it became clear that these X-rays were being drawn into this object, leading to the coining of the term dark opening. This discovery was a significant turning point, as it confirmed that dark openings were not just a product of Einstein's imagination, they were real entities that existed in space. It became apparent that we needed to study them more thoroughly. Scientists from around the world began focusing their research on a specific dark opening in the Cygnus constellation, designated Cygnus X1, which lies approximately 6,000 light-years from Earth. This dark opening was multiple times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape it. This was the defining characteristic of a dark opening: the ability to trap light within its gravitational grasp. The nature of a dark opening is simultaneously fascinating and terrifying. A dark opening is a region in space where gravity is so strong that nothing, not even light, can escape from it. Any object that ventures too close is pulled in, and once it crosses a critical boundary, it is lost forever. This inherent danger is why it is crucial to expand our understanding of dark openings. After the discovery of Cygnus X1, researchers began an extensive search for other dark openings. Estimates now suggest that there may be more than 100 million dark openings scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are extremely difficult to detect, meaning we do not have an exact count. What is clear, though, is that there could be millions of dark openings within our galaxy, highlighting their significance in cosmic research. The primary concern surrounding dark openings revolves around their gravity. Their gravitational force is so immense that anything that gets too close is gradually compressed to an extreme degree until it becomes a singularity. To put it simply, dark openings function as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most disturbing aspects of dark opening research is that if someone were to fall into one, they would be stretched into an elongated form due to the tidal forces acting upon them. This stretching would occur progressively, and the individual would perish before reaching the final stage of this process. So, to be clear, it's best to avoid falling into one at all costs. Even though the nearest dark opening is located about 500 light-years away, it still raises questions about the potential dangers they pose to us. In 2021, a remarkable achievement was accomplished when scientists successfully captured the first clear image of a dark opening. This particular dark opening was situated in the galaxy M87. The research team took numerous images over several nights, and by stitching these images together, they created a comprehensive photograph that revealed astonishing details. It turns out that a dark opening is not just a vast void of nothingness, as many people believe. In fact, a dark opening consists of three distinct layers. 1. The event horizon. Once an object crosses this boundary, there is no turning back. It will inevitably be drawn into the dark opening. 2. The photon sphere, a region where light itself can be trapped in orbit around the dark opening. Any light entering this area becomes ensnared by the dark opening's gravitational force, unable to escape. 3. The singularity, the point where everything falling into the dark opening is crushed down to an imperceptibly small point. This is where the laws of physics as we know them completely break down, making it impossible to predict what could happen. Even more intriguing and terrifying is that no two dark openings are exactly alike. While they all follow this three-layer structure, the way they function can vary significantly. Typically, scientists rely on telescopes to observe celestial objects, but with dark openings, this method is not practical. Since dark openings are invisible, researchers study them indirectly by observing the radiation they emit and the surrounding gas and dust. Sending probes like Voyager to explore a dark opening is impossible, as anything crossing the event horizon would be drawn into the singularity and obliterated. Thus, scientists must study these extraordinary objects through a two-dimensional lens despite their inherently three-dimensional nature. One theory regarding the formation of dark openings is that they result from collapsing stars. When a star exhausts its fuel, it can no longer generate the energy needed to counteract gravity, leading to an inward collapse that can ultimately create a singularity. To further investigate the nature of dark openings, NASA scientists turned their attention to the core of the M87 galaxy. Here, astronomers observed a massive whirlpool of superheated hydrogen gas rotating at an incredible speed of 1.2 million miles per hour. The sheer force of this spinning gas should have caused it to disperse, yet it remained intact. Scientists speculated that an enormous mass at the galaxy's center, weighing as much as 2 to 3 billion times the Sun's mass, was holding it together. This mass could only be explained by the presence of a dark opening. The Kerr wormhole, named after Roy Kerr, is a theoretical construct that extends the idea of a rotating dark opening. Unlike a standard Schwarzschild black hole, which has a simple event horizon and a singularity at its core, a Kerr black hole has an additional feature, a rotating ring singularity. This rotating structure could, in theory, allow for the formation of a stable passage through spacetime, potentially making interstellar or even intergalactic travel feasible. Some physicists speculate that if a Kerr wormhole were stable and traversable, it might enable instantaneous travel between distant regions of the universe or even facilitate time travel. The possibility of time travel. One of the most fascinating implications of wormholes and rotating black holes is their connection to time travel. If a wormhole connects two different points in spacetime, then theoretically, traveling through it could allow an individual to arrive at a destination before they even left, creating a paradox. Physicists call this the grandfather paradox. If someone were to travel back in time and prevent their own ancestors from being born, how could they exist in the first place? This paradox has led scientists to propose possible solutions, such as the Novikov self-consistency principle, which suggests that time loops might exist but would never allow paradoxical changes to history. While wormholes and time travel remain speculative, they continue to intrigue scientists and challenge our understanding of physics. Some researchers have proposed that exotic matter with negative energy, might be necessary to keep a wormhole open, preventing it from collapsing instantly. However, no known form of matter with these properties has yet been discovered. The future of black hole research. In recent years, advancements in observational astronomy, such as the Event Horizon Telescope, EHT, have provided new insights into black holes. In 2019, the EHT collaboration released the first-ever image of a black hole's event horizon, located in the M87 galaxy. This breakthrough confirmed many of Einstein's predictions and opened the door to further exploration of these cosmic phenomena. Future research aims to improve imaging technology to capture clearer pictures of black holes, study gravitational waves to detect mergers between black holes, investigate quantum gravity to understand what happens inside a singularity, explore the potential for new physics beyond Einstein's general relativity. The study of black holes is still in its infancy, and each new discovery brings more questions than answers. As scientists continue to push the boundaries of what is possible, the ultimate mysteries of the universe, including the true nature of space-time, gravity, and even the possibility of parallel universes, may one day be unraveled. This speculative wormhole would interface two far-off focuses in space-time, possibly, in any event, linking various universes or various moments in time. Pundits, however, contend that the CERN wormhole might be unstable or difficult to cross due to extreme radiation and the forces at the quantum level. A few physicists point out that Einstein's conditions, used to describe dark openings and wormholes, don't account for the quantum forces that govern subatomic particles. To genuinely comprehend these peculiarities, another hypothesis that joins quantum mechanics with general relativity is required. Such a hypothesis, known as a theory of everything, could explain how the universe functions at every scale, from the littlest particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for a long time. One promising candidate is superstring theory, which proposes that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is viewed as a symphony, with various particles corresponding to different vibrations of these strings. Superstring theory also provides potential explanations for dark openings, wormholes, and other exotic phenomena by demonstrating how strings twist the fabric of spacetime. Regardless of its promise, superstring theory remains highly speculative, as it requires extra dimensions of spacetime that we can't yet directly observe. These extra dimensions could be so minuscule that they are effectively invisible to us. Some scholars suggest that these dimensions were more prominent at the beginning of the universe, during the Big Bang, and that they collapsed as the universe expanded and cooled. Superstring theory's potential to explain dark openings, wormholes, and the very fabric of the universe remains one of the most exciting frontiers of modern physics. As we continue to unravel the mysteries of spacetime, dark openings, and the universe itself, there's no doubt that there is much more to learn, and perhaps even more to discover, about the very nature of reality. As we stand on the brink of such groundbreaking discoveries, one key realization remains. We are only beginning to scratch the surface in understanding dark openings and their true essence. Michio Kaku's work in the field of string theory and the ideas surrounding quantum gravity have only begun to offer potential answers. Even though we've gained a clearer picture of dark openings through technological advances, such as the Event Horizon Telescope and new methods of indirect observation, much remains beyond our grasp. The frontier of theoretical physics, particularly regarding dark openings in spacetime, is still an incredibly active area of research, where much speculation and exploration await. Despite their obvious role in shaping spacetime, dark openings have become central to discussions about the origin of the universe itself. String theory suggests that the collisions of universes could lead to the formation of new ones, and dark openings might be essential to this process. This theory could imply that our universe was born from the collision of two previously existing universes, or perhaps even suggest that we reside inside a dark opening itself, an idea that would certainly turn our understanding of the universe on its head. If this concept proves true, it could challenge everything we assume about the Big Bang. We might begin to see dark openings not just as destructive forces but as potentially creative ones, gateways to other realms or parallel universes. While the idea that dark openings could act as portals to other universes or hold the key to understanding time travel is tantalizing, it remains within the realm of theoretical speculation. The mechanics behind wormholes and the ability to navigate through them remain a major mystery. Even if wormholes are stable enough to form, the extreme radiation and forces near these structures could make them impassable. Some physicists speculate that if we could stabilize a wormhole, it might theoretically allow travel through time or between distant points in the universe. However, that remains a distant dream, at least with our current technology and understanding. Furthermore, if we examine dark openings through the lens of quantum mechanics, we encounter even more fascinating questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales. The laws of physics seem to break down entirely when we consider objects like dark openings. This discrepancy between quantum mechanics and general relativity has been one of the greatest challenges in theoretical physics. Theories such as superstring theory offer a potential framework for reconciling these differences by introducing extra dimensions and offering new insights into the nature of gravity. However, this theory has yet to be experimentally confirmed, and many of its predictions remain untested. Theoretical physicists like Kaku are working tirelessly to unify these two great pillars of physics, quantum mechanics and general relativity, into a single theory that can explain the full spectrum of phenomena across all scales. Such a theory of everything wouldn't just deepen our understanding of dark openings and other exotic objects in the universe. It could also illuminate the very nature of spacetime itself. The concept of multiple dimensions, as predicted by string theory, may help explain the hidden forces that govern the universe. It suggests that what we perceive as a four-dimensional reality may actually be just a small slice of a much larger, more complex structure. Another area of intense study is the role that dark openings play in the formation of galaxies and the larger structure of the universe. The discovery that supermassive dark openings exist at the centers of most galaxies, including our own Milky Way, raises further questions about their impact on galaxy formation and evolution. It is hypothesized that these dark openings may regulate the growth of galaxies, control the rate of star formation, and even play a role in the ultimate fate of the universe. That dark openings could have such a profound influence on shaping the cosmos adds another layer of complexity to their already mysterious nature. Additionally, the intense radiation emitted by dark openings, so-called Hawking radiation, named after the renowned physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of the information that falls into a dark opening. For decades, scientists have debated whether information is lost forever once it crosses a dark opening's event horizon, a concept known as the information paradox. Hawking's groundbreaking work suggested that dark openings might emit radiation that slowly causes them to evaporate over time, potentially resolving the paradox. However, this remains an active area of research with no definitive answers yet. What is clear is that the study of dark openings has not only provided remarkable insights into the nature of gravity, spacetime, and the universe as a whole, but has also opened the door to a new frontier in physics. Dark openings challenge our understanding of the laws of nature and continue to provide fertile ground for new theories and discoveries.